people were able to finish at least a few phases. So I wouldn't be surprised if you weren't able to finish it yesterday. It's perfectly okay. So just take your time. I did get a couple of questions from the last class. One of the questions was, a lot of people seem to think that ARM has better power performance in terms of power, and it's mostly because, I believe anyway, is because the number of transistors it takes to implement these reduced instruction sets is lower, so you're going to get lower power as a result. And Intel has mostly been focused on transistor density and speed, and they have a lot more amount of transistors that have been packed in, so that could be one reason. But there's a whole debate on it, and I encourage you guys to read the 2 articles I've posted down below. And recently, Intel's come out with a new processor called the Intel Medfield, which is supposedly closer in terms of power performance to the latest ARM chip. So that's actually the details for that processor are also listed on the Anand Tech website. So I wanted to go into a little bit more detail on branching and sort of the difference between the mode change. I had mentioned to you yesterday that in the ATPCS manual that's included in your references, it says that you can actually initiate a mode change by setting the least significant bit of the address that you want to branch to. And so that's sort of what I'm showing here. So every time you say a branch label, the PC just assigns the address of that label, or the PC is assigned the address of that label, and then it causes the branch to occur. For branch with link and BLX, branch exchange with link, what happens is you have the link register. So the link register actually gets updated with the address of the label +4, and the PC gets assigned the address of the label. And this is because you have the whole pipelining occurring. So because of the pipeline, you have to address 4 ahead. And this is all in, I'm assuming we're in thumb mode here. So when this branch with link occurs, you're assigning the link register with the address of the label +4. So when it returns, it's going to return to 2 instructions ahead, essentially. Yes, there's my typo. And this should be after VLX. Yes, thank you. So, as Galen pointed out, this should be PC +4. So what it's doing is it's going to look 2 instructions ahead of where the current PC is, add 4 in thumb mode, assign it to a link register, and the PC gets updated with the address of the label, and that causes the branch to occur. And then BLX with destination register or an immediate offset value, you have the link register gets updated with the address of the instruction right after the current BLX instruction, so it's not like +4 in this case. And this is sort of what Dave was seeing yesterday, if you remember, with the libc, CSU init. So it's just, there's a difference between BL and BLX. That's sort of what I wanted to highlight here. And the PC actually gets updated in your GDB with, if you look in GDB, you'll see the address is still even. And that's because it's actually masking the address and setting it to PC, but the T bit, which is the thumb mode bit, whether it's in thumb mode or not, gets assigned to the actual address ended with that least significant bit. So if you're in thumb mode and you want to switch to a new label, or you want to branch to a new label, what happens is if you set that least significant bit of the address, the thumb mode bit actually gets updated with that bit. So in this case, the address can be odd or even, depending on the destination mode you want to switch to. And the same thing happens with the BX. So this is why we'll see this later in the hijack lab. We have to sort of, whenever we want to jump to a method or a subroutine in the code, we have to actually set the least significant bit to 1 to ensure that thumb mode is set. So the only difference is the PC is actually going to be pointing to the link register is going to be pointing to the address after the branch instruction as opposed to +4. Oh, the last two, I'm sorry. I misunderstood your question. So the BX actually also sets the link register, so I don't see a difference there, but yes, and that was also confusing for me. So the other thing I wanted to highlight is I kind of glossed over TBB and TBH instructions. So just to make clear what those do is the TBB takes a base address register followed by an offset. It adds the offset to the value in the base register and reads only 1 byte, multiplies that by 2, and that becomes your jump target, essentially. Does that make sense? So from the TBB, it branches by an offset specified by a byte that's in the base register plus an offset. So in the bomb lab, actually, you probably saw a TBB followed by a square parenthesis and then PC comma offset. So what it's going to do there is it's going to take the offset added to the value in PC and then just read the byte there and then add 2 times that byte to the current address and then jump there. And TBH does exactly the same thing, but instead of reading a byte at that address, it reads a half word, and then so you get a larger range essentially for jumping. Does that make sense? Perfect. So we have, I think somebody asked yesterday whether we can also load bytes, half words, and other sizes of data into our registers, and the answer is we can. So you have a LDRB, STRB, where you can actually load and store bytes at a time at the destination address, and this actually allows you to do some non-aligned accesses to memory. So LDRH does half words, so LDRH, STRH does half words, and then you have LDR SB and SH, where it actually takes the sign bit of the, it takes the sign into account and extends that into the destination register. So it looks up the value at the address stored in RM, and it actually takes the sign bit into account there and puts that into, in this case it's a byte, so it's going to be putting it at bit 7. Right? So it's going to set that bit 7 to whatever the sign bit was when it read the address or the value in RM. So does that make sense? So that's for load sign byte. And similarly for load register with sign half word, it's going to take the half words sign bit into account and set bit number 15 in the destination register. right? So these are some other miscellaneous instructions that ARM also provides for ARM version 7. And these are sort of hint instructions. So Dave said that he wanted to be helped in writing programs for ARM, and he didn't want to help the ARM processor do its work, right? But this is sort of where the programmer kind of has to help out the ARM processor and help it do the optimization a little bit. So you can tell it to preload the data from a memory. And what this does is it actually allows you, the ARM processor to update its cache with values from the memory. And the memory address is actually specified in the register. So is that clear? And the next one is preload instructions, and this does exactly the same thing, but instead of looking at data, it updates the instruction. And this actually helps out the pipeline because it knows which instructions to load, and therefore it can put those in the pipeline. And unless an interrupt occurs, you know, its throughput is increased. And then finally, you have the DMB, DSB. These are two instructions for, it's called data memory barrier. These are used for synchronization, especially when you're doing it across processors, multiple processors. I know I'm not going to cover much about multiprocessing in this class, but I just thought I should put this in here. And DSB does the same thing, except it ensures the order of the operations. So while DMB is for synchronization of accessing resources, DSB actually maintains the order of operations so that nothing, you know, you don't cause a branch from what's supposed to happen, where there's no interrupts that can interfere with the order of operations. And then finally, instruction synchronization barrier is actually just a synonym for flushing the pipeline. So if you wanted to manually flush the pipeline in your code, you could do that. You just say ISB flushes the pipeline. So as I mentioned earlier briefly, there is a possibility of setting the endianness on some processors, and you can do that using this instruction, which is the set end. And there's set end BE or there's set end LE for big endian and little endian. And this only applies to data. All the processors mostly only use little endian for instructions, and some processors may allow you to change the data endianness, and in that case you would use this. And what this does is actually, it actually causes the hardware to do the calculation for you. So if you're in little endian mode, you write some data to memory, and then you say set endian BE to change to big endian, and you read the same value back. It's going to know that you had saved the value in little endian, and then read it back, and you should get the same value back, essentially. But I tend not to, I've never used this personally, because I just stick with little endian, but this is more for backward compatibility that ARM has put this in. So. Finally, save return state is an instruction that allows you to, again, save the link register and the save program status register of one mode into the stack pointer of another mode. So if you're in IRQ mode and you wanted to save the IRQ mode's link register and stack pointer, which are banked, into the stack of another mode, for whatever reason, you could use this instruction to do that. And if you remember, the stack pointer and link register are banked for each mode, so the stack can be different for each mode. So, with that being said, I'm going to talk a little bit about timing. So why is timing important, right? So if you remember our memory map from a couple slides ago, we have two hardware registers that actually include something called a watchdog timer. And I just wanted to briefly explain what a watchdog timer is and sort of what it's used for. So this is actually a hardware feature that's mostly that are included in most of the chipsets that have an ARM processor on them. And what it does is it actually counts down from a really large value down to 0, and then when if it reaches 0, it resets the board. It causes a power reset. And this was built in as a safety feature so that in case the code got into a deadlock or wasn't able to make any progress, the watchdog would kick in and literally reset the system. And these are used mostly for things like spacecraft where you have long missions, satellites, things like that, so that the code doesn't get frozen and get stuck, essentially. And so the term used for resetting the watchdog is called kicking the dog. And what you essentially have to do is to maintain a consistent state for your system, you have to reset the watchdog periodically. So that, and the consistent state is defined by the application designer or the system designer. And they basically say, if this is in a consistent state, either an IRQ or an FIQ will fire every so often, and it knows whether the system is consistent or not, and then it resets the watchdog, and so the power reset doesn't occur. And why is this important? If you remember the first Mars rover mission, which was the Pathfinder, it actually had this problem where the the rover software would keep resetting every so often. And it turns out it happened when a meteorological task, so it had a meteorological sampler on board that would take rock samples and do measurements and things. That task kept going through something called a priority inversion. So this is part of an operating system scheduler which schedules different processes. So it would invert the priority of a low priority task to a high priority so that it would run for some time and then switch back to another one. So what ended up happening was the meteorological data sampling task would get stuck doing something, and it would go into a deadlock. And the watchdog would kick in and it would reset the entire operating system. So this kept happening until they found out that they shouldn't be doing the priority inversion for that specific task, and they were able to fix it. So it's just an interesting example. So. Any questions so far? Okay. So with this, I'll do a brief introduction for interrupts. So interrupts are something that literally interrupts the control flow of the program that's running on the ARM processor. So it can be synchronous, where it's in sync with the software, and you've already seen the SWI, which is a software interrupt. That's a synchronous interrupt because it occurs in line with the code. But interrupts can also be asynchronous, where they're mostly generated by hardware. And so you can have things like A to D converters and pins going high that can trigger interrupts. And one of the examples is, we've already seen this, is the system power off reset causes a interrupt, and it actually looks up the supervisor mode's interrupt vector handler and jumps to that. And generally that loads the value of a static address into PC and starts running the code there. And Generally on ARM systems, that'll be the bootloader, so it'll start running the bootloader. But you could also have it do other things if you want it to. The other sources of interrupts are undefined instructions, which we saw for the undefined mode of ARM. Then there's non-aligned memory access. You can actually turn off this exception if you want to. If you want to allow non-aligned memory accesses, you can do that, but it's very inefficient for the ARM processor to do this. There's also non-readable memory when it gets accessed for things like trust zone. If you're trying to access a secure area of memory, you can have an interrupt that occurs. Then page faults, that's actually implemented with the virtual memory system. That's also available with some of these ARM systems. So when an interrupt occurs, you handle the interrupt using something called an interrupt service routine, or ISR for short. So you use masks on registers to enable or disable these interrupt sources. So if you remember, the CPSR actually has the I and the F flags, and the I stands for the IRQ and F stands for the FIQ interrupt. You can actually enable or disable those interrupts by setting the bit to 1 or 0. There's also a section in memory that has addresses to these interrupt service routines. So when that interrupt occurs, it causes the ARM processor to branch, or it sets the PC value to this address that's located at the interrupt vector table, which is normally predefined. And I'll go over that a little bit later. The interrupt vector table itself is located at 0 normally, but you can change that to hex FF0000 by setting a bit in the system control register that I talked about a couple of slides back in CP15. You can also wire the handler by directly writing code at that table. And that's generally what happens is you'll have one instruction in the interrupt vector table that usually has LDR, PC, PC plus offset. And we'll see that example. So here are the different exception types that can occur. You have reset, and when a reset occurs, it changes the mode to supervisor mode for the processor, and the vector address it looks up is 0. And this is the highest priority interrupt. The lowest priority is undefined instruction, and it switches the processor to undefined mode and looks up in the vector table at hex 4. And this is actually the lowest. SWI is actually slightly higher priority, even though it's the same number on the table. And so you have, so actually this is what it would look like. Your interrupt vector table, the memory, again, I have it increasing upwards. So it starts off at 0. So whatever is located here, some microcontrollers for even ARM will actually just have an address at that location. But most of the modern processors like Cortex-M3, Cortex-A will actually have an instruction there which it will execute. So it sets the PC to 0 when a reset occurs and starts executing that instruction there. So if an IRQ were to occur, it looks up hex 18 address and runs whatever is there. And generally, as I mentioned to you earlier, the SWI or any of these will have the same value. Generally, you'll see LDR, PC, PC100. And so the PC, when it's pointed to hex 8, what it'll happen is it'll look up hex 8 plus hex 64, which is decimal 100, add the 2, and load that into PC, and then jump to your SWI handler code, which is located in hex 6C. And here you can actually write a full-on piece of code, because here you don't have much space, you just get one instruction. And this was done for legacy reasons again. So the interrupt vector table has been a feature for a lot of microcontrollers since back in the day. So that's why now the way to do it is you actually have this LDR PC100 instruction located at that vector table, which will start running code for the SWI handler. And you can actually start hooking up these SWI handlers so that once it gets to here, you actually don't have a lot of room because if you know, here the same thing will happen. So if a prefetch abort were to occur, it will just take hex C, add that to hex 64, and jump to that address. So you don't have a lot of space to write your SWI handler code. So generally what you do here is you do a branch with link to another piece of code, right? And so that way you can actually have more instructions run when that interrupt occurs. So if you remember, I'd shown you guys the CPSR actually has the mode as the first 5 bits. And each of the modes have the following encodings, which are up on the table. The ones we've seen so far are supervisor mode. When a SWI occurs, the mode actually changes to binary 1, 0, 0, 1, 1. And when it switches back to user mode, it just has 1, 0, 0, 0, 0. So when an exception occurs, what the processor does is copy the CPSR into the SPSR of the mode that you're switching to. The CPSR then reflects the new mode that it's in, whether it's user or supervisor, and then it disables any further interrupts from occurring. This is usually done in your handler code, as we'll see later. And you can actually re-enable the interrupts if you want to when you're in the interrupt handler. That can lead to some very interesting side effects. And then it stores the PC +4 for ARM or PC +2 for thumb into the link register of the mode. So this is the PC that is in the mode that you're jumping from, not the PC of the mode you're jumping to. The PC of the mode then finally gets updated to the interrupt vector table address, right, that we had seen earlier. So this is what happens when the exception occurs. Any questions on this piece? Pretty clear? So it's no, so the only thing that's saved from the old is the PC into the link register of the new mode. Okay, so if you remember, the stack pointer and the link register are banked for each mode, which means they have their own stack pointer and link register. So the PC of the old mode gets saved into, actually, go back here. Yeah, so if you remember, so each mode has stack pointer and link register and an SPSR. So what will happen when a mode change occurs is it copies the CPSR of your mode that you're in, let's say we're on user or system, and copies it into SPSR. And it also copies the PC +4 +2 into the link register of the mode that you're jumping to. And then it updates the PC, since there's only one PC, to the address of a location in the vector table. So it'll update it to 8 for SWI, it'll update it to C for prefetch abort, and so on. Does that make sense? All right. So once that happens, when we want to return, so ARM is generous enough to copy the CPSR into the SPSR, but it's our responsibility to copy the SPSR back into the CPSR. And so, if you remember, we had talked about this one instruction, special instruction, either moves PCLR, or you could also use subs PCLR. And the S suffix there, what that does is it actually copies the SPSR back into the CPSR for us, while simultaneously copying the link register into the PC, or link register minus offset into PC if you're using subs. So, so this is a way to do both essentially in one instruction. and you kind of have to use that a lot. So because there's if you were to copy the CPSR first and then branch using copying the link register into PC, the CPSR mode changes, right? And so you're back in the different mode, but you don't have access to the link register of the mode that you were coming back from. So this is sort of the way of doing the interrupt handling. So when an IRQ exception occurs, the IRQs are generally disabled. You can re-enable them. When an FIQ exception occurs, both IRQ and FIQ, so both those flags in the CPSR are disabled. And each mode's link register is going to have the previous EC plus 4, but the PC itself is going to point to the address of the handler in the vector table. So it's not gonna, the PC is not going to update itself to the vector table plus 2 or plus 4, so you don't have to worry about that. So if you remember here, when the PC gets updated, it gets updated to this address. It's not going to take the SWI plus 4 or plus 2, just to avoid that confusion. So that should be pretty straightforward. And the data aborts exception mode link register has actually PC plus 8 as opposed to PC plus 4. And this is both for ARM and Thumb. This is something weird that I found out just by reading online. So I haven't tried it myself yet, so it would be interesting to find out. So what does an IRQ handler look like? So let's say we have a hardware signal that's been wired up to a pin, and we have the IRQs enabled, and we basically trigger the IRQ when the pin goes high, right? So in ARM mode, this is what the code would look like, but you basically have to save all your registers R0 through 12 for IRQ. If you remember, IRQ doesn't have a lot of banked registers. Actually, it has none of the R0 through R12 banked. And so it's our job to save those onto the stack so that we don't lose the information for the user mode or system mode. So once that's done, then we can go on to branch to a secondary interrupt service routine for IRQ if you want to, or you can actually write the code in here itself. And here you can also re-enable IRQs again to have another IRQ occur while it's executing this IRQ handler. But at that point, you have to make your handler something that's called re-entrant, which means no matter where you are in the IRQ handler, if it were to go back to another IRQ were to occur, the state for this IRQ handling would be saved on the stack, right, before that new IRQ gets handled, essentially. So you can have IRQs within IRQs, and you can have nested interrupts. But you just have to make sure your code is re-entrant. And once you're done using writing your code for IRQ, you load the registers back from the stack into R0 through 12. And then you do a sub-S PCLR. We had seen that we can also do a move PCLR, but in this case, they're actually subtracting link register -4. I just thought I'd show an example where they're using sub-S PCLR instead of move S PCLR for returning back to system mode. Yep. So here they're doing it because there's a branch with link that's occurring to the secondary IRQ handler. So here what's going to happen is your PC is going to point 2 instructions ahead, right, when you're in this mode. So the PC first started off with the vector table address. Then it loads PC plus offset, right, and at that point the pipeline's going. And so you're going to have the PC pointing 2 instructions ahead, and when you branch to this secondary IRQ handler, the link register is actually going to be the link register of the PC from this IRQ handler. So this is actually showing a nested interrupt handler. And so you have to subtract 4 to essentially, otherwise it's going to point directly to here, and when you do a sub-S PCLR down at the bottom, it's going to be pointing to the link register, I believe it's going to point to here. So. Okay, I think I know why this happened. So I believe this was because since the PC was pointing 2 instructions ahead when you came to the IRQ from the user mode or system mode, right? You don't, when you jump back, you have to subtract 1 instruction essentially to jump back to the instruction that's right after where the interrupt occurred. Okay, so when you register the link register here, it's going to be taking the link register that you stored on the stack. It's not going to take this calculation into there, yeah, it shouldn't be. Okay. Right. I'm guessing this was for making it re-entrant, so it was an attempt at making yeah, in case it got interrupted in the middle. So. All right, so this is something that got changed from your slides that you have. There's an additional line here that I've added. And so this is what a sample FIQ handler would look like. So if you remember, in IRQ mode, when you have an IRQ interrupt occur, it disables only the IRQs. But when an FIQ occurs, it disables both the IRQ and the FIQ. And we can actually re-enable those interrupts here, but generally for FIQs, you don't re-enable them because FIQs are meant to be really fast and handled appropriately fast. So in this case, you only save R0 through R7. If you remember our banked register set, we have R8 through R14 are actually banked for us, which means we have less number of registers to save to the stack. So we only have to save R0 through R7, and that essentially makes the FIQ handler a little bit faster, if you will. So. All right, and so once you've saved your registers to the stack, you can re-enable your interrupts. You can handle your interrupt handler. You can write the code here. And once you've done that, though, you have to, you can re-enable IRQs, and that's sort of the example I'm giving here. So what it's doing is it's actually testing if IRQ mode has been re-enabled already. And if it hasn't, it's using the compare, and if you remember the conditional mnemonics from yesterday, it's using bit clear if not equals. So it compares and tests if IRQ mode has been set, and if it hasn't been set, then it optionally re-enables the IRQs. Actually, no, because if you remember, so once it's set the CPSR here, once you do the PCLR, you're going back to yeah, I think this example, I was trying to go back to the regular mode and whatever was set in when it came into the IRQ or the FIQ handler. So it's just going to take the SPSR and whatever mode it was running in, right? And if you had IRQs and FIQs enabled when you came into this mode, it would restore that state back, as opposed to actually, once you re-enable it, all that's doing is it's allowing more interrupts to occur while just this FIQ handler is being run. And once you restore it back, right, So you could save that back to the CPSR if you wanted to, but generally we want to return to a state that's been that was as it was before we entered this FIQ handler. So. Yes, so this was actually an older notation. So all that means is the exclamation is right back. So when it's doing LDMFD, if you remember, it was doing LDMIA, and it's going to take those registers from the stack and then update the stack pointer back to where it started. So it's essentially doing a pop, but the stack pointer has been updated to include all these registers, and when it's done popping, it has to update the stack pointer back to before it entered this routine, right? So that's what it's doing here. So the exclamation is for write back, and the caret symbol actually is the old notation for doing pre-indexing. So you notice I'm not doing the square brackets.
Okay. So it's just...
Yeah. So it's just pre-index with write back. Essentially. It's a good question. This was actually ARM v5 and prior. So this is just reiterating what I talked about earlier, which is most of the ARM hardware actually defines these vector tables, and they're indexed generally by the exception type. So SWI, you'll find it hex 08, and so on and so forth. And actually, the SWI instruction encoding allows for 24 bits that aren't used at all. So when you do a SWI, the instruction only uses up, I think, the first 8 bits. The 24 bits are not used. But what you can do is you can actually differentiate between different SWIs. So if you wanted to do the Linux kernel and you want to do the syswrite difference between syswrite, sysexit, you can actually use those 24 bits to differentiate the SWI. And the way you do that actually is you actually reference the link register, and the link register, you're going to access the instruction right after where the interrupt occurred, the SWI occurred essentially. And since this is a synchronous interrupt, you can actually load the value of the link register -4, which is the instruction prior to where the SWI occurred. The instruction that occurred to, the instruction that's after the SWI essentially is the link register. And when you subtract 4, you're going to be pointing to the SWI instruction itself. And if you have the SWI followed by some number, it actually encodes that into the instruction, right? So it's going to use up 8 bits for the SWI, 24 bits for the number that you specify. And then you can actually use that number to differentiate between different SWIs. So an example is if you have SWI followed by some other instruction, right? You're going to have, you can say SWI with hex 18. And that's going to go to the vector table at hex 8, look up LDR PC PC100. That's going to run the SWI handler, which was at 6C, if you remember the diagram earlier. And it's going to start running this code. And in the SWI handler, we can jump to somewhere like hex 108 because we want bigger code length, right? And we can't fit everything in 100 bytes or whatever was given to us by the vector table. So once we jump to 108, what happens is the link register will actually be pointing to, in the mode that you're in, will be pointing to the instruction right after the SWI. So what you can do is you can actually load the value for this instruction. So this entire encoded instruction gets put into R0. Then you mask out the SWI encoding, which are the first 8 bits, and the rest of it will get you hex 18. And so now you're able to, in your SWI handler, actually get this value. And then based on that, you can actually branch would link to the SWI handler and switch based on the SWI number. So what this allows you to do is you can differentiate between syscalls now using a number. So if you say SWI x4, that's for syswrite, versus SWI 0 or whatever it is for exit, right? And you can differentiate between the different SWI handlers. Is there any question on this? Even though the emulator that you're using doesn't do it that way, if you remember we used just a SWI with a 0, you can actually use a number there and it'll get encoded into the instruction. And you can use it to differentiate in your kernel between different SWIs. All right, so this brings us to the interrupts lab. So for the interrupts lab, actually, we won't be using the QEMU emulator that, with the setup for Linaro. We'll actually be using it with a bare metal simulator. And we're actually simulating an ARM 926 EJ chip, which is an earlier architecture. It's actually ARM v5, but I just thought it would be good to get a feel for how these interrupts work. We'll be emulating a serial driver using the UART. And in order to see something interesting from our keyboard input, we'll just add 1 to whatever character is input. So what we get out will be a different character. It'll be just added +1. So to do this, actually, let me switch here. For this lab, you'll have to go into a different folder. You can actually shut off QEMU. If you go into your host's projects directory, there is an interrupts folder. You go to CD interrupts. There's going to be 2 binaries here, build and run build. And in order to emulate, you have to first build this code, which is what the build script is for. And then if you do run build, it'll actually run it in QEMU. And then you can test by, on the host terminal itself, you start typing characters and you should see output. Even though it'll open a blank QEMU screen, you can just minimize that. So all it's doing is it's actually placing the code that we have here, along with the .ld file is actually a linker script that specifies the memory map for the ARM 926 EJ, because we're trying to actually emulate a bare metal hardware. So you will be modifying vectors.s and inter.c. The adding 1 part is actually the easiest part. The more interesting part will be modifying vectors.s, which is where you write the reset handler. So what happens on a power reset. And I've actually added comments in there to sort of guide.